Hello everybody, today we're going to talk about the idea of heat and its role in the first law of thermodynamics. Now, we all have a fairly intuitive idea of what heat is. For example, if we are sitting outside on a sunny day, we seem to be able to feel the heat coming from the sun and entering our bodies. We can feel the temperature of our body increasing. Likewise, if we are holding a block of ice or a snowball, we seem to be able to feel the heat leaving our hands and going into the snowball. We can feel the temperature of our hands falling. And in many ways, this is actually kind of like a sixth sense, because it's not like you sort of touch the heat, but that's not what we're talking about. So, what we can intuitively say is that heat is a form of energy which flows from hot things into cold things. And already we can make the following statement, which is that heat, represented by the letter Q, is energy, represented by the letter E, in transit. Now, there are two important points we have to make about this statement we've just made. The first is that although all of our observations seem to suggest that heat flows from hot things into cold things, that's not always the case. For example, your freezer at your home, that has a very cold box, and what we're actually doing is sucking heat out of that box. We are taking heat from the already cold freezer and ejecting it into the warmer surroundings of the room. So certainly it seems that there are instances where heat can travel not from hot to cold, but from cold to hot. But the important thing is that in the case of your freezer at least, what we have to do is supply electricity to it. We have to put energy into the system in order to transfer heat from a colder body to a hotter body. And all the natural examples we seem to have are from heat spontaneously going from hot to cold and not from cold to hot. So that's the first point we have to make. The second point we have to make, just as important, is this line here, in transit. So it makes no sense to say some body contains X amount of heat. There is no gauge or scale which a body has which tells us how much heat is in that body. Heat only makes sense in transit. So let me give you an example. If it's a cold day and your hands are cold, you can warm them up in two different ways. In one way, you can hold them out next to a fire and you can feel the heat going from the fire into your hands and the temperature of your hands will increase. Or another way is you can rub your hands together. You can put work in, you put energy into the system, and that work causes friction, and that friction causes the temperature of your hands to increase. Now, the important thing is that in both those examples, the temperature of your hands has increased. And there is no physical difference to the state of your hands, whether it's heating them by holding them next to a fire or heating them by rubbing together. There is no physical difference between those two things. And that brings us neatly onto the first law of thermodynamics. So, that heat is a form of energy might seem obvious today, but this was certainly not always the case. In fact, it was Lavoisier in 1789 who put forward a theory that heat was actually some weightless fluid called caloric, which cannot be created or destroyed and flows from body to body. And this was the generally accepted view for a long time. It wasn't until Joule in the years 1840 to 1845 that he was able to experimentally demonstrate that heat is just another form of energy. And the way he did this was by means of two different experiments. Now, the first experiment, he took a wheel with many paddles in it, submerged in a big vat of water, and he connected this to a rope with a mass at the end of it. And what he did was he allowed the mass to fall, so it changed the gravitational potential energy of the mass. It put work into this paddle, which then started rotating. And he did this several times, and he measured the temperature difference of this body of water. And then he did another experiment. He took a resistor connected to a battery, as you see here, and he put energy into the battery through the resistor, and he measured the heat output from this resistor, which we now know to be I squared R. So what he did was he found that the energy he put in, whether it was from a falling mass connected by a rope to a paddle, or from a battery supplying energy into a resistor, the energy he put in was equal to the heat he managed to get out. And he showed that by means of these two wildly different examples. And because the heat out is equal to the energy in, no matter the form of that energy that you put in, that was his way of demonstrating that heat is totally equivalent to energy, that heat is actually a form of energy. And then it wasn't until a little bit later that Mayer and then Helmholtz were able to take these observations and put them into a concrete law, the first law of thermodynamics. And that's what's written up here. Energy is conserved, and both heat and work are forms of energy. Now, energy is conserved is maybe one of the first physical laws we all learn at school, right? But that's only part of the law. Heat and work are both forms of energy. So some system, whether it's a block of ice or a box of gas, has some internal energy which we write as U. Now, U is a function of all the internal degrees of freedom that that energy possesses. So for a box of gas, that would be, say, the momentum of each molecule in that box of gas, and also the gravitational potential energy of each molecule in that, the electromagnetic potential, all these different things. This internal energy is a function of all these internal degrees of freedom that our system possesses. And what we can say is that the change in internal energy, which we write as delta U, delta just means the change of, so the change in internal energy is equal to delta Q, which is the heat supplied to the system, plus delta W, which is the work done on the system. And you'll often see the first law written out like this. The point is that when we have our system with internal energy U, we can either supply heat to the system or we can supply work to the system. But whichever we do, by the time we've done it, the internal energy of that system has changed, and we have literally no way of telling whether we supplied work to the system or heat to the system. They are both forms of energy, they both change the internal state of that system, and there is nothing to distinguish once the event has happened which of these two things we did. And that is the first law of thermodynamics. And just like our hand example, we can warm them up, we can change the internal energy of our hands by either rubbing them together, doing delta W, doing work, or by holding them next to a fire, putting heat into them, putting delta Q into them. But once we've done those things, all we can have is the temperature of our hands having increased. And once we've done that, no one can come look at our hands and say, oh, you held them next to a fire, or oh, you rubbed them together. Heat is a form of energy, and energy is always conserved. And that is the only thing that the first law of thermodynamics says. But it is remarkable how much you can deduce from this alone. And in future videos, we will get onto that. So thank you very much for watching. I really appreciate your support. I think in the next video, what we're going to do is look at temperature a bit more closely and maybe try and come up with a statistical definition for temperature and what that is really all about. Thank you.